Here's a question. How much of your material handling system is officially designed, and how much is currently wearing safety shoes?
That's a surprisingly useful question, because many workstations continue working long after they stop being intentional.
Right. And the mission for this deep dive is to increase our observational capability around that exact idea. We're going to do that by examining a single, rather powerful field note on industrial movement.
Hmm.
And the governing insight we're exploring today is this. Sometimes the workstation is not moving material through the process. The operator is.
Yeah.
And I think to fully grasp that, we really have to rethink what we're actually looking at when we walk a facility floor.
I agree. That distinction is subtle, but it fundamentally changes how you view an operation. Because when we look at a factory floor, our eyes are naturally drawn to the massive infrastructure.
Exactly.
We see the heavy machinery, the overhead conveyor belts, the automated guided vehicles humming along their magnetic strips. We see the engineered systems because they are loud, they are expensive, and they take up space.
Right. They demand your attention.
They do. But what we often fail to see is the human logistics network, the one operating entirely under the radar, connecting the physical gaps that the engineered systems left behind.
So let's start with what we can actually observe, assuming we can strip away all our biases. If we stand on a floor and focus purely on the physical reality of the work, strictly avoiding any immediate urge to, diagnose a problem or pitch a solution, what do we actually see?
Well, we see a work cycle.
Right. But if we break that cycle down into its most basic, literal actions, we aren't just seeing assembly. We're seeing an operator walking 2 steps to retrieve a piece of material.
Yeah.
We're seeing them turning 90 degrees to access a specialized tool. We're seeing them reaching beyond a comfortable distance to grab a fastener and bending to collect a component from a lower rack.
And it's the sheer frequency of those actions that demands our attention, because if you observe a line worker closely for just 10 minutes, you'll often notice them crossing the workstation multiple times in a single work cycle.
Right.
And individually, isolated in a vacuum, these movements appear entirely insignificant. Taking 2 steps to the left to grab a bin, or pivoting to reach a pneumatic drill, it doesn't look like a system failure.
It just looks like standard work.
It looks like standard work. But collectively, over the course of an 8-hour shift, these movements form a hidden physical constraint on the entire operation.
I want to push back on that a little, or at least get a sense of the scale you're talking about, because taking a couple of steps doesn't sound like a constraint. But the field notes we're reviewing mention that in some unoptimized distribution environments, this unbudgeted transit can result in operators traveling up to 12 miles a day?
Yes.
12 miles. That sounds almost impossible inside a single facility unless you're a forklift driver. Are we talking about massive warehouse pickers or line workers taking 2 steps at a time? Because those feel like very different things.
Well, it sounds staggering until you do the math on repetition. We aren't necessarily talking about a picker walking end to end in a 1,000,000-square-foot facility, though that certainly happens.
Sure.
We're often talking about localized assembly or packing stations. Imagine an operator whose cycle time is 45 seconds.
Okay.
To complete that cycle, they have to walk 5 feet to a parts bin and 5 feet back.
10 feet total.
10 feet total. Doesn't seem like much. But they do that cycle 80 times an hour.
Oh, I see.
So that's 800 feet an hour. Over an 8-hour shift, that single round trip to one bin is over a mile. Now add the trip to the tool rack.
Right.
Add the walk to the quality inspection gauge. Add the steps taken to discard packaging. Those 10-foot increments compound into an invisible commute happening entirely within a 50-square-foot box.
That is a profound way to look at it. An invisible commute. It essentially highlights how a static workstation can quietly transform into a logistical transport route. The operator is no longer just assembling a product or picking an order. They've been conscripted into the material handling system. And because they're wearing safety shoes rather than running on a wired electrical grid, the facility doesn't track the cost of that transit in the same way it tracks the energy consumption of a conveyor motor.
Exactly. If a conveyor motor is running 20% longer than it needs to, a sensor trips. An engineer gets an alert, and someone adjusts the belt tension or the logic controller.
Right, there's a dashboard for that.
There's a dashboard. But when an operator walks an extra 3 miles a day, no alarm goes off. The system simply absorbs their biological energy to keep functioning.
Which brings up a really useful mental model for how we look at this. We can view it through the thermodynamics of human motion.
Yes.
If we look back at early industrial engineers, like Frank and Lillian Gilbreth, who literally broke human work down into micro motions they called third legs.
Right, things like search, find, grasp, and position.
Exactly. If we use that lens, we stop seeing a static workspace. Instead, we see a dynamic geometry. If you look at it thermodynamically, isn't every step taken to retrieve a tool actually a leak in the system's operational energy?
It's a thermodynamic loss, pure and simple. When the spatial geometry of the workstation fails, the human body is required to expend energy to bridge the gap.
Wow.
Every unnecessary reach, every twist of the spine, every step away from the center line of the work is an expenditure of biological energy that yields zero value to the final product.
If it's this obvious of a leak, though, it makes me wonder how these spaces evolve in the first place. Workstations rarely start out deeply flawed. When the engineers draw them up in CAD software, everything looks perfectly efficient.
Right.
So how do we get to a point where a worker is walking 12 miles a day in 10-foot increments?
Well, it's an evolution.
Right.
And it happens gradually and invisibly over time. The evolution is almost archaeological.
Archaeological, I like that.
Yeah, let's say you have a line assembling control panels. 6 months into production, a new subcomponent is introduced to the product. A box of those new components is placed wherever there happens to be an open square foot of space on the line.
Makes sense.
Then maybe a specific torque wrench is moved temporarily to the other side of the bench to accommodate a short-term custom run. A few weeks later, an extra scrap container is added by an operator simply because the main one fills up too fast.
And none of these are malicious or negligent decisions.
Yeah.
They're highly localized adaptations to immediate practical needs.
Exactly. They are problem-solving in real time. But here's the catch. Because the operator acts as a highly adaptable infrastructure, the work continues successfully.
The product still gets made.
The panels still get assembled, the quality checks still pass, and the orders still ship on time. Because the output hasn't dropped, the new cluttered arrangement rarely attracts any managerial attention. The operator just silently adapts. They absorb the extra walking, the reaching, the turning. They physically connect the gaps. And over time, those temporary, informal workarounds calcify into the official workflow.
That is a fascinating dynamic. Repetition is what creates the invisibility here. Because the cycle repeats continuously, the gradual accumulation of small, extra movements becomes impossible to see on a standard performance spreadsheet.
Yes, exactly.
If you're a floor manager looking at a screen, the spreadsheet shows that the cycle time is still roughly on target, or maybe just slightly degraded. But the spreadsheet has no mechanism to explain the physical cost of maintaining that cycle time.
We talk a lot about lean manufacturing waste. The Japanese term is muda, and usually we talk about it in terms of wasted material or waiting time. But there's a deep biological symmetry to muda that we miss when we only look at spreadsheets.
What do you mean by biological symmetry?
Well, unnecessary reaching and bending aren't just abstract operational inefficiencies. They are physical stressors. Reaching for a bin at full arm extension isn't just a lost second of production. It's a microtax on the operator's shoulder joint.
Ah, I see.
By hour 6 of a shift, that physical tax degrades fine motor control. It introduces process variability. A worker who is physically fatigued is going to drop more screws, strip more threads, and miss more visual defects.
You know, I have to say, it's quite an observation to note that some temporary storage locations remain temporary for longer than some management initiatives.
It's universally true. A bin placed just for the afternoon often becomes a permanent, immovable fixture of the process architecture. The operator simply builds a physical habit around it, subconsciously compensating for the spatial friction until they don't even realize they're reaching anymore.
This creeping inefficiency makes intuitive sense, but it makes me wonder, at what point does a slightly annoying reach or an extra 2 steps cross the line from a productivity leak into an actual occupational hazard?
That's the real question.
Because the occupational safety authorities actually draw a boundary here. Introducing the single piece of verified evidence we pulled from the source materials for this deep dive. OSHA specifically notes that ergonomic interventions can reduce unnecessary movement and physical demands, and that simple, low-cost solutions are often available.
That's a very deliberate boundary they're drawing. And it's incredibly useful for our observation. It allows us to completely reframe how we view the concept of ergonomics.
How so?
Well, often ergonomics is mistakenly viewed as a human resources concession to comfort.
Right, like an anti-fatigue mat.
Exactly. We think of it as buying a softer mat to stand on, or issuing a nicer chair, or maybe providing a back brace. But based on that OSHA note regarding the reduction of unnecessary movement, we should actually reframe ergonomics as a discipline of precision.
A discipline of precision.
Yeah.
That changes the goal completely. You aren't just making the operator comfortable, you are methodically eliminating spatial friction.
Precisely. You are engineering the space so that the human body operates within its optimal power zone. The hands stay between the shoulders and the waist, the elbows stay close to the torso, and the feet stay planted.
Which raises a critical question about resource allocation in these facilities. Do organizations get too caught up in heavy capital expenditures while completely missing the simple, low-cost solutions that OSHA is pointing out?
All the time.
It feels like we are quick to invest in new robotics, complex software integrations, or massive automated storage and retrieval systems to save time. But sometimes the most mathematically effective intervention is simply moving a high-use tool 3 feet closer to a worker's natural reach zone.
It's a massive operational blind spot. Capital expenditures are highly visible. Buying a $1 million robotic arm represents definitive, measurable action that a management team can put on a slide deck.
Right, it looks good in a quarterly review.
Exactly. Moving a tool balancer 36 inches to the left is almost entirely invisible to upper management, yet it might save an operator from executing a compromised shoulder rotation 400 times a shift.
Wow.
If we treat ergonomics as a discipline of precision, then spatial proximity becomes one of the most critical metrics of facility performance.
Okay, so let's talk about how we actually measure that spatial proximity.
Yeah.
Because if this invisible commute is so hard to see on a spreadsheet, how does an observer actually spot it without shutting down production or setting up a dozen cameras?
Yeah, that's the practical challenge.
The author of the field notes we're discussing developed a practical diagnostic tool for this, called the 5-step motion map. And let's be clear up front, this is a diagnostic tool designed purely for immediate visibility. It's a quick field exercise, not some validated, peer-reviewed engineering standard.
Yeah.
It's simply a way to force your eyes to see the invisible commute.
The entire methodology is grounded in forced observation. Step 1 is simply to sketch the operator's movement path for one complete work cycle. You just draw a simple top-down view of the workstation on a blank piece of paper.
And the reason you do this on paper, rather than just standing there watching, is because drawing the lines physically forces you to see the web of movement.
Exactly. When you watch it live, the movement disappears the moment the operator stops moving. When you draw it on paper, a path that crosses the same empty space 3 times starts to look like a dark, heavy line of ink. You are mapping the friction.
That makes total sense.
Which brings us to step 2. You mark every reach, every turn, every bend, and every walk. You actively document the physical interactions between the human and the geometry of the space.
So step 1 is mapping the path. Step 2 is marking the specific physical stress points, the bends and twists.
Yes.
Step 3 is to identify the items touched most repeatedly. You're isolating the high-frequency variables in the work cycle.
Yes, you are separating the core tools from the exceptions. A scanner they use on every single part is a high-frequency variable. A calibration weight they use once a shift is a low-frequency variable.
Okay. Then step 4. Compare whether those highly touched items are actually located at the point of use. Are the tools and materials where the hands naturally fall when the operator is in a neutral posture? Or does the operator have to travel to them?
And finally, step 5. Reposition just one frequently used item closer to the point of use and observe the next cycle. You don't redesign the whole bench. You move one scanner, you slide one parts bin 12 inches forward, and you watch what happens to that heavy, dark line of ink on your paper.
From an operational standpoint, how does this localized pen and paper exercise relate to broader industrial engineering practices? It feels like a micro version of something much larger.
It very closely mirrors the concept of trip matrices used by premium manufacturers in advanced facility design.
Trip matrices.
Yeah. When engineers are laying out a new multi-million-dollar factory, they build a mathematical matrix tracking the frequency of trips between 2 points, say between a machining center and a quality lab.
Okay.
The fundamental rule of trip matrix is that the pairs of locations with the highest interaction frequencies must be placed closest together on the floor plan. The five-step map is essentially a localized, manual version of that advanced mathematical modeling.
Oh, brilliant.
It completely bypasses the need for complex simulation software and allows any observer, a supervisor, a safety coordinator, or the operator themselves to immediately identify spatial friction in their immediate radius.
You know, it's funny, when you think about it that way, you start to realize that a workstation occasionally develops a routing strategy that nobody formally approved.
Oh, absolutely. By constantly adapting to bad layouts, the operator's physical travel pattern often becomes the most thoroughly tested yet entirely unintentional transport system in the whole facility.
Yeah.
They are walking a path that was never engineered but is executed with absolute punishing consistency.
But hold on, I need to play devil's advocate here and introduce a critical limitation. We are prioritizing observation first and diagnosis second. A movement map reveals opportunities. It reveals the heavy inclines, but it doesn't automatically establish the root cause of the layout.
That's true.
We have to acknowledge that movement does not automatically equal waste.
That is a vital nuance, and it's where well-intentioned continuous improvement efforts often go off the rails.
So?
Well, if we observe an operator walking 10 steps away from their primary station to place a finished part on a specific staging rack, it is incredibly tempting to pull out our five-step map, label that walking as inefficient, and move the staging rack right next to the bench.
Right, to eliminate the steps.
But there may be highly valid constraints at play that aren't immediately visible.
What kind of constraints?
Safety requirements, for one. Those 10 steps might exist to keep the operator outside the swing radius of an automated forklift route. Or strict quality controls might dictate that the staging rack must be located next to a specific ventilation hood.
Oh, I see.
There could be facility resource sharing. Maybe two different lines need to feed parts into that exact same rack. Or there might simply be immovable physical space constraints, like a load-bearing column hidden inside a wall.
This brings us back to systems thinking. We have to ask, what if the movement we are observing is actually perfectly rational given the environment?
Yes.
If we blindly eliminate a walking step without understanding the broader ecosystem of the floor, we might accidentally bypass a critical safety check or a necessary quality inspection point.
Exactly.
We might optimize a local movement only to degrade the overall systemic output, or worse, put someone in danger.
This is precisely why visibility must precede intervention. The primary goal of the five-step map is not to immediately dictate a physical change. The goal is to give you the data to ask why the movement exists before you attempt to engineer it away. We must inspect the geography before we try to change the person. If the geography dictates the movement for a valid reason, like a safety buffer, we accept it and work around it. But if the geography dictates the movement simply because a bin of parts was left there 3 years ago during a product changeover, then we alter the geography.
If someone gave you 10 minutes tomorrow, what would you inspect?
One work cycle, one sheet of paper, one movement path. I'd start there. Because sometimes the shortest path to improvement is finding out why the current path became so long.
Next time you walk the floor, look closely at the smallest local restriction: a misplaced bin, a slightly constrained tool cord. Large industrial systems are remarkably cooperative. They will quietly reorganize an entire facility's workflow around one tiny overlooked problem.
Are your people doing the job, or are they just transporting it?